Good morning students. Welcome to 11th standard physics class. Today's topic is on propagation of sound waves, unit 11. Propagation of sound waves. We know that sound waves are longitudinal waves and when they propagate, compression and rarefactions are formed. In the following section, we compute the speed of sound in air by Newton's method and also discuss the Laplace correction and the factors affecting sound in air. Sir Isaac Newton assumed that when sound propagates in air, the formation of compression and rarefaction takes place in a very slow manner, so that the process is isothermal in nature. That is, the heat produced during compression and heat lost during rarefaction occur over a period of time such that the temperature of the medium remains constant. Therefore, by treating the air molecules to form an ideal gas, the changes in pressure and volume obey Boyle's law. Mathematically, we can write PV is equal to constant. Differentiation equation P dV plus V dP is equal to 0. So, P is equal to minus V dP by dV. Here, Vt is equal to square root of Bt by rho is equal to square root of P by rho. Rho is density of liquid. The P is the pressure of air whose value NTP. NTP means normal temperature and pressure. Laplace correction. In 1816, Laplace satisfactorily corrected this discrepancy by assuming that when the sound propagates through a medium, the particles oscillate very rapidly such that the compression and rarefaction occur very fast. Hence, the change of heat produced due to compression and cooling effect due to rarefaction do not take place because air is a bad conductor of heat. Since temperature is no longer considered as a constant here. Sound propagation is an adiabatic process. By adiabatic consideration, the gas obeys Poisson's law, which is PV or gamma is equal to constant. So, gamma is equal to Cp by Cv. This is ratio between specific heat at constant pressure and specific heat of constant volume. Differentiating equation V gamma dP plus P gamma V gamma minus 1 dV is equal to 0. This equation is called Laplace correction. The next, characteristics of progressive waves. Particles in the medium vibrate about their mean position with the same amplitude. The phase of every particle range from 0 to 2 pi. So, no particle remains at rest permanently. During wave propagation, particles come to the rest position only twice at the extreme points, the end points. Transverse progressive waves are characterized by crest and trough, whereas longitudinal progressive waves are characterized by compression and rarefactions. Suppose we give jerk on a stretched string at time t is equal to 0 second. Let us assume that the wave pulse created during this disturbance move along positive x direction with a constant speed v. We can represent the shape of the wave pulse. Mathematically, y is equal to y of x, 0. So, it is equal to f of x at time t is equal to 0. After some time, t the pulse moving towards the right and any point on it can be represented by x power dash. Y of x, t is equal to f of x is equal to f of x minus vt. Let us graphically represent the two forms of the wave variation. One, space variation or time variation. By keeping the time fixed, the change in displacement with respect to x is plotted. Let us consider a sinusoidal graph y is equal to a sin of x, where k is a constant. Since the wavelength lambda denotes the distance between any 2 points in the same state of motion, the displacement y is the same both sides. Next, superposition principle. When a jerk is given to a stretched string, which is tied at one end. A wave pulse is produced and the pulse travels along the string. Suppose two persons holding the stretched string on the either side give a jerk. Then these two wave pulses move towards each other, meet at some point, and move away from each other with their original identity. Their behavior is very different only at the crossing or meeting points. This behavior depends on whether the two pulses have the same or different shape. When the pulses have the same shape at the crossing, the total displacement is the algebraic sum of the individual displacements, and hence its net amplitude is higher than the amplitude of the individual pulses. To understand mathematically, let us consider two functions which characterize the displacement of the waves. For example, y1 is equal to a1 sin kx minus omega t and y2 is equal to a2 cos kx minus omega t. Since both y1 and y2 satisfy the wave equation, then the algebraic sum y is equal to y1 plus y2. Interference of waves. Interference is a phenomenon in which two waves superimpose to form a resultant wave of greater, lower or the same amplitude. Consider two harmonic waves having identical frequencies, constant phase difference pi, and same waveform A1 and A2. Then they move simultaneously in a particular direction. Then interference occurs. Y is equal to y1 plus y2. The next topic is formation of beats. When two or more waves superimpose each other with slightly different frequencies, then a sound of periodically varying amplitude at a point is observed. This phenomenon is known as beats. The number of amplitude maximum per second is called beat frequency. If we have two sources, then the difference in frequency gives the beat frequency. So number of beats per second, n is equal to modulus f1 minus f2 per second. Characteristics of stationary waves. Certain points in the region in which the wave exists have maximum amplitude called as antinodes, and at certain points the amplitude is minimum or zero called as nodes. The distance between two consecutive nodes or antinodes is lambda by 2. The distance between a node and its neighboring antinode is lambda by 4. The transfer of energy along the standing wave is 0. Stationary waves in sonometer. Sona means sound related and sonometer implies sound related measurements. It is a device for demonstrating the relationship between the frequency of the sound produced in the transverse standing wave in a string and the tension, length and mass per unit length of the string. Therefore, using this device, we can determine the following quantities. Frequency of the tuning fork or frequency of alternating current. Second one, the tension in the string. Third one, the unknown hanging mass. Construction. The sonometer is made up of a hollow box which is 1 meter long with a uniform metallic thin string attached to it. One end of the string is connected to a hook and the other end is connected to a weight hanger through a pulley. Since only one string is used, it's known as monochord. The weights are added to the free end of the wire to increase the tension of the wire. Two adjustable wooden knives are put over a board and their positions are adjusted to change the vibrating length of the stretched wire. Working. A transverse stationary or standing wave is produced and hence at the knife edges P and Q nodes are formed. In between the knife edges, antinodes are formed. If the length of the vibrating element is L, then L is equal to lambda by 2. In cross multiplication, lambda is equal to 2L. Next, laws of transverse vibrations in stretched strings. There are 3 laws of transverse vibration of stretched strings which are given as follows. First one, the law of length. For a given wire with tension T and the mass per unit length mu. The frequency varies inversely with the vibrating length. Therefore, F inversely proportional to 1 by L. So, F is equal to C by L. Here, C is constant. Then second law, the law of tension. For a given vibrating length L and mass per unit length mu, the frequency varies directly with the square root of the tension T. So, F directly proportional to square root of T. Here, F is equal to A square root. A is constant here. Next, the law of mass. For a given vibrating length L and tension T, the frequency varies inversely with the square root of the mass per unit length mu. So, F inversely proportional to 1 by square root of mu. So, F is equal to B by square root of mu, where B is a constant here. Next, intensity of sound. When a sound wave is emitted by a source, the energy is carried to all possible surrounding points. The average sound energy emitted or transmitted per unit time or per second is called sound power. Therefore, the intensity of sound is defined as the sound power transmitted per unit area taken normal to the propagation of the sound wave. For a particular source, the sound intensity is inversely proportional to the square of the distance from the source. So, I is equal to power of the source by 4 pi r square. So, I inversely proportional to 1 by r square. This is known as inverse square law of sound intensity. Next
loudness
topic
is
loudness
two
of
sounds with the same intensity.
Two sounds with same intensity need not have the same loudness.
The sound
for
here
example,
during
the sound here during the explanation of silent closed loop is very loud when compared to the same explanation in a noise market. Though the intensity of the sound is the same, the loudness is not. If the intensity of sound is increased, then loudness also increases. The degree of sensation of sound produced in the air or the perception of sound by the listener. Next, vibration of air column. Musical instruments like flute, clarinet, nadaswaram, etc. are known as wind instruments. The work on the principle of vibrations of air columns. The simplest form of a wind instrument is the organ pipe. It is made up of wooden or metal pipe which produces the musical sound. Look at the picture of a clarinet. It's a pipe with one end closed and the other end open. If one end of the pipe is closed, the wave reflected at this closed end is 180 degree out of phase with the incoming wave. Thus, there is no displacement of the particles at the closed end. Therefore, notes are formed at the closed end and antinodes are formed at open end. Frequencies higher than fundamental frequency can be produced by blowing air strongly at open end. Such frequencies are called overtones. Okay students, today's topic is over. Today's homework. Students, I have given homework. Read the questions and answers well and write 2 or 3 times in your classwork note. After writing, you send the answer to me. Okay students, thank you. God bless you all.